Good morning, class. This is the second video on formula manipulation. You might recall that in the last video, we went through the even numbered problems on this document, beginning with problem 2 and finishing here with problem 26. So I'd like to begin with problem 28. We're going to complete together from 28 through 40 even in this lesson. Okay, so I've got them all set up here. Here's problem 28. In problem 28, we're going to be solving for R1. So the first thing to do, I think, is to isolate 1 over R1. So in so doing, I will need to use subtraction. The opposite of addition is subtraction. So we end up with this. 1 over R1 is 1 over RT minus 1 over R2. Now this is not a formula for R1, however. It's a formula for its inverse. So what we're going to do is make this a proportion. So we have to combine these two fractions into a single fraction. You might remember that when you add or subtract fractions, you need a common denominator. So here the denominators are RT and R2. So a common denominator would be the product of R2 and RT. Okay, 1 over RT is the same thing as R2 over R2 RT. You see, if you were going to reduce this fraction, you would cancel out the R2s and you'd get back this fraction here. Okay, similarly, in taking this fraction and transforming it into this one, you can see the denominator got multiplied by RT. Thus, we must multiply the numerator by RT, like this. So these fractions are equivalent. Now that we have a common denominator, of course, we can combine this into a single fraction. The numerator of that fraction will be R2 minus RT. And now we have a proportion because we have a single fraction on the left and a single fraction of the right. So we can maybe use cross multiplication to solve this. So if I want a formula for R1, I'm going to multiply this way first. So R1 multiplied by the binomial. So here we'll need a bracket around the binomial is equal to, now we can multiply this way. This is R2 times RT. Times 1, right? Okay, and finally, remember we want a formula for R1, so we'll finally change from the multiplication here to division on the other side, and we will have the product over some formula for two parallel resistors, like that. Okay, so again, first we isolated 1 over R1, and then the key to solving this was to get a common denominator so we could subtract the fractions. Once we had a single fraction on the left and right, we had a proportion, so we used cross multiplication, and then we isolated R1. Okay, here's problem 30. We want to solve for f, and there are all kinds of obstacles. There's the big square root sign. Of course, there's the number 1 and the k and the square on f here. So let's one by one eliminate these obstacles. So I think first we'll get rid of the large square root sign here. Since the square root is isolated, we can start by squaring the left side and the right side. And that will give us this. Okay. Now, I think that what we'll do is isolate the term that contains the f next. All right, so how can we do that? We can move the 1 to the other side. If we do that, we'll be left with the negative of this term. Okay, or we can move this term to the left side because then it would be positive. So like this, n squared plus k over f squared is 1. Okay, so from subtraction to addition. And now continue to isolate this term by subtracting n squared. So k over f squared is 1 minus n squared, like that. Now, the item we're solving for is in the denominator. So we know that we can use this strategy here to get it out of the denominator. Okay, and you might remember we've used that for other questions here. For example, number 4, which was much more simplified, but in any case, we did use that strategy. Okay, so when we multiply though by f squared, once again, this is 2 terms, binomial. So we have to bracket like this. Isolate f squared. So we take the multiplication implied and change it into division. So we divide by 1 minus n squared to isolate f squared. So that is our next step there. And finally, moving from f squared to plain old f requires taking the square root. So we will have the following as our final result. Okay, so that's our formula for f. So look back. First, we eliminated the large square root sign by squaring the opposite operation. Okay, then what we did in the next couple of steps was we isolated the term k over f squared. So that was the term containing the f. That's why we isolated it. We got it out of the denominator. Then we isolated f squared itself so that we could finally square root to get f. Okay, next. Question 32. So this is gain is equal to 10 times the logarithm of power out divided by power in. Now, this quantity here is called the argument of the logarithm. Okay, so this is one single unit here. This is called the argument of this common logarithm. And the logarithm itself, you can find it on your calculators. Mine is a Casio. Here's the logarithm. And while we're looking at the calculator, let's remember that when we're doing these problems, we're always looking for the inverse operation, the opposite operation, such as multiplication and division are opposites, addition and subtraction are opposites. What is the opposite of the common logarithm? The calculator gives us a clue. Right above it in yellow on my calculator, you should see 10 to the x. 10 to the x is the inverse of the common logarithm. The common logarithm has base 10. Okay, anyway, so we're going to try to solve for power in. So the first thing to do is isolate the logarithm itself. So this involves beginning by dividing by 10. So g divided by 10 is equal to the logarithm of power out divided by power in, like that. At this point, if we're trying to get at the argument in here, we have to eliminate this common logarithm. So here is when we use the inverse function. Remember, it is 10 to the x, 10 to the x. This is the x. So the left side will look like this, 10 to the x, like that. when we do the inverse logarithm on the right side, all that will be left is the argument of the function itself, okay? So going from this step to this step means taking the inverse logarithm of both sides of the equation. Treat this as the x in 10 to the x. Okay, remember what we're solving for is power in, so we use this little multiplication now to get that variable out of the denominator. So power in multiplied by 10 to the g over 10 is equal to, the only thing left on the right side now will be power out. So finally, in isolating power in, we'll change from multiplication to division on the right side. So power in is equal to power out divided by 10 to the g over 10. Just like that. Okay, so first, divide by 10 to isolate the logarithm. Then eliminate the logarithm by taking the log inverse of both sides. Get the variable out of the denominator and then divide. Okay, problem 34. This one is pretty complicated here. So what we have is solving for time, which represents, how long will the switch be closed in the circuit. So we're going to try to isolate little t here, realizing that it's part of the exponent on the exponential function. So e to the x, this whole thing is the x on e to the x. So back to our calculator real quickly. E to the x is up here on my calculator in yellow. It's the second function on the ln function, or the natural logarithm. So the natural logarithm and e to the x are inverses, and we're going to need to use that concept in this solution. But first, as we're making our way to the little t, we can start by eliminating some of these things. So first, let's move the r. How do we do that? Of course, by multiplying. So I times r. Like that. Next step, eliminate this e. So this shows multiplication, so we do division. So I times r divided by e. Like that. Now, the bracket around the binomial is no longer necessary since there's no longer anything in front of the binomial. So we can just have it like this. Okay, now we're going to isolate this little unit right here now because it is the unit containing the t. So how will we do that? I think I'm going to bring it to the left side so that it can be positive. So first, I'm going to add it. That leaves 1 here. Okay, so it went from subtraction on the right to addition on the left. And next, I'm going to isolate this by moving this to the other side where it will be subtracted. Okay, so again, going back, first we removed the things in front of the bracket. Now we've isolated the unit that contains little t. Okay, now we're stuck. It's kind of like this function back here, where at this point we had to eliminate the common logarithm. Once again here, we're at the point where we have to eliminate the exponential function. How do you eliminate the exponential function? By performing its inverse, which is the natural logarithm. if I take the natural logarithm of the left side, I will have this. Therefore, I must also take the natural logarithm of the right side. And that looks like this. Just take the logarithm, natural logarithm of the binomial that was sitting there. Okay, so that's the step where we had to remember what the inverse of e to the x is. Okay, now again, we're still working away here. Let's isolate negative t next. Just change from the division here to multiplication like this. So the negative of t is L over R multiplied by the log of the binomial, like that. And very last step, all we have to do is change from a negative t to a positive t, and this is done simply by multiplying both sides by -1. So we get negative L over R times the natural logarithm, like this. And finally, that problem is complete. Okay, so in solving for t, first we moved the items in front of the bracket, like that got us to this stage. Then we isolated the exponential function, that got us to this stage. Here's the key step: eliminate the exponential function by using the natural logarithm, and then continue until t is isolated. So these problems today, you can see, are more involved certainly than the ones we did in the first lesson on this topic. Okay. Oh yes. If you take a quick look at 36 and 38, you'll see that the variable you're solving for is in two different places. So we must understand how to do this type of question as well. If you look at 36, it's a proportion, one fraction on the left and one fraction on the right. So how can we solve the proportion? By using cross multiplication. So let's start like this first. Then we will have m1 times k1 equals, now go this way, and it's k2 times, we need a bracket here, m1 plus m2. Like that. We need a bracket because it's two terms, a binomial. Now, what we're solving for is m1, and there's one here and one here. For this one in the bracket, let's open the bracket. So we're going to have m1 k1 is, this term will be m1 k2 plus this one here, m2 k2, like this. Within each term, the order doesn't matter. If you want to write the k first and then the m, that would be the same thing. But the key is that we still have one m1 here and one m1 here, and they are separated by the equal sign. So what we have to do is get them on the same side of the equation. So I'm going to put the terms, so this is like collection of like terms. So the two terms with m1 I'm going to have on the left side. So that means subtract here, like this. And now you can see, oh, there's m1 and there's m1. The only way to now solve for m1 is to use common factoring of m1. So m1 is what we're trying to solve for. We remove it as a common factor from the two terms here. When you do this, you have to divide the two terms by m1. So that will leave k1 minus k2 in the bracket. Do a quick check. If you were going to open up this bracket like this using the distributive property, you should certainly get this line back. And again, the reason we did that is because now the M1 is only in one place instead of in two places, right? Two places, two places, two places. So that common factoring is required when we need to ensure that we get our variable only in one place so that we can do the last step, which will be dividing by K1 minus K2. There we go. It's a formula for M1. And certainly M1 is not present in the right side. All right, so look at what we did. We had a proportion. We started by cross multiplying, opening up the bracket, and then we collected like terms. The two terms with M1 were brought to the left side, and this is the all-important step. This is called common factoring. So common factor M1 from the left side so that we can then solve for M1. Okay, let's go on to the next problem here, which is problem 38, and it's rather similar to 36. Again, we're solving for R1. It's in two places. Okay, the left side isn't a fraction, but we're still going to solve just by starting like this. Okay, so it's similar to the start here, which was cross multiplication. So RT is going to get multiplied by the binomial, put it in a bracket. And now we're solving for R1. There's one here and one here. Open up this bracket. So it's RT R1 plus RT R2. Or R1 RT plus R2 RT. The order in the term doesn't matter, okay? Those can be reversed. Anyway, the point is we're trying to solve for R1, and there's one here and one here. We have to collect like terms. So I think I'll take the terms containing R1 and put them on the right side. So this term can stay where it is. This term can stay where it is. The only term moving is this one. When it moves to the right side, it will be subtracted. Okay, so it's RT R1 or R1 RT. And now we have to do this step right here, the common factoring step. We're solving for R1, so we common factor it like this. Okay, so I'm going to write down again here that is what we are doing. We are common factoring. When R1 is removed from the terms, we will be left with in here R2 minus RT. So you use division, divide each term by R1 to fill in this bracket. Remember, check it quickly. If you were to open the bracket up, you must get this back. Okay, last step, get R1 by itself, so divide by the binomial. So RT, R2, or R2, RT, whatever order you like, that doesn't matter. And underneath will be R2 minus RT. And there is our formula for R1. Okay, so 36 and 38 are very similar in that the variable begins in two places, and our objective is to get that variable on one side of the equation so that it can be common factored. Okay, we're going to do one last problem together, and it's this one. Work is equal to force times distance times the cosine of theta, and we're going to solve for theta. Cosine of theta is a single function. So we begin by isolating that trigonometric function. How do we isolate it? We use division. So we're going to divide work by force and by distance. Okay, W divided by Fs, like that. And now we have the trigonometric function isolated, the cosine of theta. That's pretty good, but we want an actual formula for theta. So how do we go from the cosine of theta to theta? We need to know what the inverse function is. Just like we saw earlier today, the inverse of the common logarithm was 10 to the x. The inverse of the exponential function was the natural logarithm ln. What is the inverse of the cosine function? Well, it's just cosine inverse. So if you look on your calculator at cosine above it, mine is in yellow, it says cosine inverse. So that's what we do. We go from cosine of theta to theta by simply taking the cosine inverse of, in this case, W divided by Fs. And now that one is done. Okay, so in the video today, I went through some pretty involved examples we did from 28 through 40 even. So I've now completed all of the even numbered problems with you in this document. So of course, all of the odd ones within the document are left for you to try now on your own. I will be posting full solutions in Blackboard to accompany all of those odd numbered problems. Okay, so please give those a try. Have a great day.